is grouped into two groups, which is the first one is half wave rectifier, and then the second one is full wave rectifier. So for the half wave rectifier, we already discussed last week about. I hope you still remember what is the basic diagram of the half wave rectifier circuit. And for this week, we will discuss about center tap full wave rectifier, which is divided into two, which is the first one, center tap full wave rectifier, and the second one is also full wave rectifier, but it's called as a bridge rectifier. So from this slide, we can, even though they are grouped into one type of rectifier, which is full wave rectifier, but in terms of configuration, in terms of electrical connection is different. So from this center tap full wave rectifier, there is two diode attached together, but for bridge rectifier, there are four. One, two, three, four diodes, which is connected in one circuit. And in this diagram, there is a one particular, I think the component, which is capacitor. So for bridge rectifier, it can be divided into no common or normal bridge rectifier, and another one is a filter bridge rectifier. So a full wave rectifier, we can classify, or we can define it as a device that has two or more diodes. So this is the group as I showed before, which is we have center tap and also bridge rectifier. So that with this kind of diode arrangement, the loads current flow in the same direction during each half cycle for the AC supply. So in terms of output and input, because the rectifier, they will rectify the AC power source. So the original of AC signal is sinusoidal shape. And when they have a half wave rectifier, we already discussed that there is a one on and another diode will serve as off, and the shape is like this for the half rectifier. For the full wave rectifier, because there are two diodes or four diodes attached together, so each diode will take place during each half cycle for the input signal. So in other words, full wave rectifier uses the full output for both half cycle of the transformers. So in this slide, I want to introduce to you about the basic features of the bridge rectifier, in which we can see that a bridge rectifier, they will have four uh, diode here. Okay, so the bridge rectifier will have four diodes, which is connected in a bridge network, and the diodes conduct in a diagonal pairs to give a full wave pulsating DC output. So diagonal pairs, that means one set opposite diode will on, and another set opposite of diode will turn off. Okay, why? Because forward bias to on and reverse bias will cause the diode to be off. So another advantage for the bridge rectifier, they only needs less turn of wire in the transformers during the winding process, and the transformers used in the rectifier is versus a two diode full wave rectifier will be small and lighter, and also because of the less number of turns, the cost would be less. So this will give the advantage of rectifier, which is outweighs of using diodes instead of two in a conventional two diode full wave rectifier. So the full wave rectifier actually do not use center tap transformers. Okay, so because of this, their DC output is equal to the input of voltage from the high voltage secondary of the power transformers. Okay, so we can see from here that VP will be the same with the same value with the V input. And also, the bridge rectifier can produce twice the voltage at the same size of transformers. So the last figure here is about the symbol of a diode. I think you should remember this one, which is at the end of the angle, the triangle is a cathode, and the opposite one is anode. Okay, so we want to discuss further about bridge rectifier. So as I mentioned before, bridge rectifier will have two half cycle. So in some books, they will say or they will denote as a first half positive, and the second half will serve as negative cycle. So the voltage input will be supplied to the diagonal opposite corners of the network, and the output will be taken from the remaining two corners. So in this diagram, we have D1 opposite with D2 and D4 opposite to D2. So you can see from here, these two pairs will be off once D2 and D3 is on. So this is the AC supply. So we can redraw this diagram, convert into this diagram, which is we have point A for the positive and point B for the negative. So if the transformer is working very good, so there is a positive terminal at the point A. Okay, so here is our point A, and a negative potential will be supplied to for point B. Okay, because of this power supply. So the positive potential, okay, positive potential at point A will cause D3 as a forward bias, because we can see that positive terminal of power supply attached to the positive terminal of diode. So this connection will create or leads to the forward biasing of D3. Meanwhile, for D4, because of this positive terminal of A is attached to a negative terminal of D4, that means D4 will act as a reverse bias. So the negative potential at point B will create a positive, will connect to the positive terminal of D1, and therefore D1 also in forward. But for D2, the positive terminal of negative terminal will create the reverse bias for the D2. So at this time, D2 and D1, we already know that they will have a, uh forward bias. And when the diode is a forward bias, the current will
Doctor,
flow.
this slide is not moving for us.
Really?
Yeah, we're still stuck at the second slide.
Wait, wait. I will
Okay.
restart. Just now we stuck at what? At which slide?
The second slide.
Second slide. You mean this one?
Yes, doctor.
This one?
Yeah.
So I need to start again. Right. Okay, never mind. Can you see my slide now?
Yes.
Okay. So, okay. This one, this slide, just want to introduce the type of a rectifier in which we will discuss this half wave rectifier. We already discussed the half wave rectifier, and also in this week we will discuss about the full wave rectifier. Is it moving the slide?
No, doctor.
No, doctor.
Hmm.
Doctor, I think because you press the present slide on the PowerPoint.
Yeah, like last week we already did the same thing, right? I think I need to. I thought I want to record. Maybe I stop recording. Hmm. How about like this?
Yeah,
Yes.
yeah, we can see.
Basic features. Can you see the basic features of bridge rectifier?
Yep.
Yes.
Okay. So now I want to change in apa slideshow tengok. Can you can see or not? Here? Can you see when I scroll the slide?
No.
No, doctor.
Oh. Okay, so in that case I need to present like this. Right.
Yes.
Yes.
Yes, doctor.
Okay, thank you for the feedback. I will try. But I punya pen pula tak function.
I think because you present you need to present whole screen maybe, doctor.
The whole screen. Okay, I will try the whole screen.
Entire screen.
Okay. Entire screen, right?
Yeah.
I try. How about now?
Yes,
Yes,
doctor.
yes.
Oh, so now the you can see when I scroll down the slide.
Yeah.
The slide
Yeah,
can.
doctor.
Okay. Okay. Never mind. Can you hear my voice?
Yes.
Yeah.
All
Yes.
right. So just now you listen to the audio, but you cannot see the visual. So now I show you the visual about the rectifiers. Okay, so for rectifier, actually we can group them into two groups, which is the first one is Okay, the first one is half wave rectifier, and the second one is full wave rectifier. For half wave rectifier, we already discussed in last week. So for this week, we will discuss about full wave rectifier, in which it has two types. The first one is bridge rectifier. Why they call it as a bridge rectifier? If you see from the diagram of this rectifier, there are four diodes attached together. Okay, so and you can see that the direction of the diodes, they have two set of a pair of diode, which is D1 is pair with D2, and D3 is pairing with D4. Okay, I mean the direction of current flow. So for the second type of full wave rectifier is center tap full wave rectifier. Means that center tap is referred to the type of the transformer that been used in this type of rectifier. So when we say center tap, that means the connection of the rectifier is start at the middle of the transformer. Okay, and we can say that full wave rectifier, we can define it as a device that has two or more diodes that arrange so that the load currents will flow in the same direction during each cycle of the AC supply. So that's mean full wave rectifier will have first half and the second half cycle. And in terms of waveform, we know that we are using AC input signal. That's mean AC stand for the alternating current. That's mean the signal of the input should be in the sinusoidal form. And this the top image here is the half wave rectification process, the waveform for the half wave rectifier. And for the full wave rectifier, the shape of the waveform is totally different, and we cannot see the flat region here because it's filled with the component of the second pair of diode during the uh, suppose off state for the half wave rectifier. So in other words, that full wave rectifier will use the full output, both half cycle of the transformer. So now I want to talk about basic features of the bridge rectifier, in which there are few good features about bridge rectifier. The first one, we already know that they have four diodes that connected in a bridge network, like in electronics lab, you learn about the Wheatstone bridge, something like that. And then the diode will conduct in a diagonal form to give a full wave of pulsating DC output. Okay. And also for the transformer, they only need a transformer with a minimal number of turns of wire, and therefore this kind of a bridge rectifier is lighter and also smaller compared to conventional rectifier, and the cost is less. So this full wave rectifier, the bridge rectifier did not use any center tap transformers, which is high voltage secondary, and also this DC output is equal to the input voltage from the high voltage secondary of power transformer. This one I already explained in the second slide. And then another plus point for bridge rectifier, it can produce twice the voltage with the same size of transformers. So this is the shape of the output voltage form for full wave rectifier, especially for the bridge rectifier. And I also want to remind you about the symbol of diode, in which we have the cathode and the anode, as shown in this slide. So we want to focus on the bridge rectifier. So first of all, we look at the first half cycle for bridge rectifier, in which we know that the input of the circuit is applied to the diagonally opposite corners in the of the network, and the output is taken from the remaining two corners. So here is the AC input signal for this rectifier, and we can also redraw this diagram into this, in which we will know that the process of the current flow, which is from A to the load and then return back to the transformer. So here, uh, first of all, we notice that the direction of D3 and D1 is the same. Meanwhile, D4 and D2 is opposite to D3 and D1 arrangement. So let's say the transformer working properly, and there is a positive potential at terminal A, and negative potential at the terminal B. So the positive potential at terminal A will cause two things. The first one, the positive potential at terminal B will cause D2 become forward bias, because positive terminal of power supply attached to the positive terminal of diode. And the second one, because of positive terminal at positive potential at terminal B will cause reverse bias to D4. That means the current only can flow through the D3 from point 1 to point 2. Okay, but the current cannot flow from point 1 to point 4, because of this D4 is reverse bias. That means it will stop the current to flow through it. So at this time, D3 and D1 is forward bias, and allows the current to pass through them. Meanwhile, D4 and D2 is reverse bias, and there is no current flow through it. And then the path from for the current will flow from point 1 to D3 up through the load, and return back flowing to point 4 to 3 and go back to B. Okay, so this is the signal for the input, and this is the signal for the voltage output for the first half cycle. Okay, but because they have four diodes, they have two pairs of diode. So we need to consider for the second half cycle. So the same process will repeated, and then but the polarity across the secondary of the transformers will create a forward bias for the D2 and also D4, but reverse bias the D3 and D1. And then because of this process, the current will flow from point B to uh, point 3, go to D2, and then go to point 2, and then go to the load. through the secondary of transformer. I mean the point one point the transformer, and then go back to the point A. So at the same time, D2 and D4 is forward bias, and then the current will flow through line 3 2 and enters to the load's resistance, and then return back to the source flowing to 4.4, which is here, to 1, and then go back to 1 to A, sorry. So and from these two cycles, we know that this is the input waveform, which is a sinusoidal type. And then for the input voltage form, they have Vmax and also negative Vmax, and also we have time. And then this diagram, okay, for the first half cycle, and this one is the output voltage for the second half cycle, because both diagram is meant for full wave bridge rectifier, and then when we combine these two diagram, finally we will have the full output waveform for full wave bridge rectifier. Okay, so the next part is about the diode type that been used in the full wave bridge rectifier. So there are two types of diode we can use. The first one is ideal diode, and the second one is practical diode. So when we use ideal diode, that means the input voltage will be exactly the same with the output voltage. Okay, and for the practical diode, for example here, because we are using silicon type of diode, that means the voltage barrier for these two diode is 1.4 volt. Okay, and then the peak for the voltage at the out signal will be deducted by with 1.4 volt, because of the voltage barrier. So another part about the rectifier is peak inverse voltage. Okay, so what is the meaning of peak inverse voltage, which is PIV? This PIV parameter actually refer to the maximum of the reverse voltage that a junction or diode can withstand without damage. Okay, so the maximum voltage at the reverse voltage for a diode to withstand without any damage. Okay, so we look at the first diagram, which is this diagram is using diode model, ideal diode model, and we know that forward bias diode, which is for D1 and D2. Okay, so we can get the PIV equals to VP out. Okay, and for D3 and D4 here, this pair will have a peak inverse voltage, which is equal to the peak secondary voltage. Okay, so because we know that the output voltage is ideally same with the secondary voltage. Okay, for the second part, for this diagram we are using practical diode. So when we said practical diode, that means we need to consider the type of semiconductor that developed during the fabrication of this kind of diode. So for this case, we know that the diode is is made up from silicon, which is they will have a potential barrier of 0.7 volt. That's mean the PIV for this configuration, we can have a VP out plus with the 0.7 volt. Okay, because PIV refer to the maximum of the reverse voltage before it damage. Okay, and then we also can use simple mathematical analysis to discuss full wave rectifier, because we know that the voltage for AC we can write as VI equals to Vm sine omega 3, and then we have current 1, and then we have current 2 for the first half. For the second half, so actually the signal is about the same. When we write for I1, we can have the maximum of current, and then sine omega t for this region, which is from theta and from 0 until 180, and I1 equals to 0 for this angle. Okay, and for the I2, the same thing, in which I2 equals to 0 for below or equal to 180, and we can write I2 equals to Im sine omega t for the pi omega t in between, or same with pi to 2 pi. And we also can calculate DC or average current, which is referred to the average value of the output current. So here we consider current DC. Okay, and the formula, okay, this is how we derive IDC equals to 2Im over pi. Okay, so you can see here that Im over pi for rectifier is double the the value of half wave rectifier. Okay, so the next part is DC output voltage, which is referred to DC output voltage across a load. Okay, so because in full wave rectifier, we will have at the end of the circuit, there is a load there. So VDC can be calculated by multiply IDC with RL. Okay, and then we know the IDC, and then we insert the formula into this equation, and then we can calculate VDC equal to 2Im RL over pi, and for the RMS what we call current. Okay, so the formula is this. Okay, and Im over square root of 2. So the next parameter we can calculate is rectifier efficiency. So very simple formula for rectifier efficiency means that we know the power of DC over power of AC, and then we will get the value. And then lastly is a ripple factor, which is ripple RF. Suppose RF here. F equals to I RMS, okay, here, and then over IDC, okay, and then we can get Im over square root 2 over 2Im over pi. So that is a full wave rectifier for the type bridge rectifier. So now we move to center tap rectifier. Okay, So as I mentioned just now, center tap rectifier is known as a center tap because of the center tap transformer. So this diagram is center tap rectifier, which is also known as a conventional full wave rectifier. So we can see in this diagram, they have two diode, which is D1 here and D2 here. And in between of these diode separated by one load. Okay. And in some cases or some books, you also can see this type of diagram. Okay. In which they put the resistor at the end of the circuit, but still if you look at carefully look at this diagram, actually we can shift this RL in the between of two diodes here. Okay, so the center tap refer to this part, okay, in which we divide these two lines into two parts, which is the first half and the second half. Okay, and the anode of the diode will connected to the center tap secondary winding, and the cathode of the diodes are connected to the load resistor. Okay, so the first one is during the positive half, and this diagram is for second half. Okay, so we will look into first half, which is during positive half cycle. Okay, so here these two diagram is similar, and when we put the input AC diagram, AC supply to here, so the secondary winding of the center tap transformers will divide this input, which is AC voltage, into the two parts, which is the first one positive and the second one negative. Okay, how it happen? So for positive half cycle of the input AC signal, point A here, okay, will be positive voltage, and the terminal B, of course, will be negative voltage, and the center tap will be 0. And the positive terminal connected to the P side. Okay, again, you have to refer to the connection of power supply to diode. Okay, so very clear from here that positive potential is attached to the positive side of D1. And for D2, the negative terminal B is connected to the N type of diode uh, D1. Okay, so that's mean D1 will act as a forward bias during the positive half cycle. So definitely when the diode is in forward bias, it will permit the current to flow. Okay, for the negative terminal, the diode D2 is a reverse bias for the during the positive half cycle, and then no current will flow through it, and the current will flow only in the upper part as marked in this diagram, while the lower part there will no current to the load because of reverse bias. Therefore, during the first half cycle of the AC input signal, only D1 working and allow the current to flow in the circuit. Okay, and then for the negative half cycle of the input signal, the same thing, we just change the polarity when the terminal A become negative and terminal B become positive. And again, center tap will be grounded and there is a 0 volt there. And negative terminal will attach to the P side of D1 here. And positive terminal here will attach to N side of D1. And sorry, this one supposed D2. And therefore, the D2 is a reverse bias during, sorry, correct. Okay, and then D1 is reverse bias during the negative half cycle and does not allow the current flow to it. So the same thing for a negative half cycle, current will flow only at the lower part of the circuit and zero current will exist in the first upper part of the circuit because of the forward bias and reverse bias of D2. Okay, so now there is a simple calculation for center tap rectifier, but the first the top curve here, which is the input signal. Okay, when the input signal, this one for the output signal for D1 and D2, and when we mix these two, add it, these two profile for D1 and D2, and then the final of the output is like this. And then there are simple calculation for center tap rectifier in which we can calculate VDC as 2Vm over pi, and VDC we can get from Vp minus B, and VB refer to the built-in voltage. I think you should know what is built-in voltage there, times with 2 divided by pi. And also we can calculate the IDC, which is through the load. IDC equals to VDC over the load, and then we can substitute the VDC formula into this part, and finally we will have 2Vp minus Vb over pi RL. So for the next part is a ripple factor, in which we can calculate as this equation here. Okay, and then lastly is root mean square voltage. For this formula, Vrms equals to V peak over the square root 2. Okay, so this slide is about center tap transformer. Okay, actually it's not popular topic actually to discuss, because normally we will focus on the center tap and also center tap rectifier, not the transformer. But for the engineering student, maybe they will study on that. Okay, so this one, the function of this kind of transformer will increase or reduce the AC voltage as what we know, which is a transformer function is to increase or decrease. And then this is a secondary apa? Secondary winding of the center tap will divide the input signal or the out AC signal into two parts. Okay, and this light is the summary of terms that we can use for half wave rectifier, center tap full wave rectifier, and bridge full wave rectifier. Okay, so the summary of number of diode that been used for half wave is only one, and two for center tap, and bridge is four. Okay, and the tapping definitely only for a center tap full wave rectifier, but the formula for the PIV, which is the maximum voltage can be applied to the rectifier. For half wave is V maximum, and for center tap 2 maximum maximum potential, and the last one is VM. And the next part is average or DC current for half wave and full wave. They only difference in term of number two. The formula will be is the same, only for the full wave double the signal of half wave. And for DC voltage also the same thing, which is full wave will have double of the DC voltage for the half wave, and for RMS every rectifier look like the same, the formula, but the difference only over 2 and over square root 2. Okay, okay or not? Tidur ke apa? Are you okay?
Jarang tak okay.
Okay, doctor.
Okay, good. Okay, so the next part is about a rectifier with a filter. Okay, so the figure A is full wave rectifier. We know that AC signal in and then come out as a DC. So for half wave, this one will be empty or flat. But for full wave, they have like this. Okay, so in the second diagram, this is rectifier with a filter. So output a ripple. Okay, so that's mean we can see smoothing effect happen in this ripple signal after they put filter. So normally this filter is made up from capacitor. And again, in some cases, they have one capacitor. And in other cases, they will have two or triple capacitor. So the number of capacitor attached to the full wave rectifier will affect the ripple signal. Okay, so the rectifier with filter is called as a capacitor input filter. So this type of device, they will use the same concept of full wave, but they attach with the capacitor input to filter the signal from the full wave rectifier before it go to the load. Okay, that is why for this diagram you can see this is rectifier, half wave rectifier, and then this one capacitor before it goes to the uh, load. Okay, so during the first quarter cycle, suku. Okay, so the quarter cycle of the input here. Okay, so what happened? Okay, we know our diode normally is silicon type. That means they will have a barrier of 0.7 volt. So that's mean during the first quarter cycle of the input, the diode is forward bias, and then the capacitor can charge within 0.7 volt of the input peak. Okay, so here the practical diode is using because we consider the voltage built-in voltage in the diode. Okay, and I think you know what is capacitor is. Is a device that can store the energy very fast, can charge very fast, and store the energy. So once the input voltage in the circle, Vp in increase, that's mean the capacitor start to store the energy in it. And then when the input voltage decrease here, okay, suppose when they increase and then go down, the current or sorry, the voltage also declining. But because of the attachment of capacitor here, once they reach the maximum Vp in maximum here, it will store the energy in the potential in the capacitor. So while it go down, the signal of input go down, the energy that stored in the VC, the capacitor will, oh sorry, uh, will decrease slowly due to the resistor attachment. That means it start to deliver the energy or the burden or the loads, reduce the energy stored in the capacitor versus time. So again, the slightly decrease of this line is due to the decrement of energy, stored energy in the capacitor. But when the input voltage increase up to the Vp in maximum here, then when it's over the voltage or the energies exist in the capacitor, it will charge up again the capacitor. That is why in this signal, the output, you can see there is a increment in the plot of the V output. Okay, so this process continue. Okay, so we can see the variation in the capacitor voltage, which is due to the charging. Okay, the charging is from V input, and the discharging come from the load, which is will create a ripple voltage here. So you can see the large ripple voltage means that less effective of filtering process. But with a small rippling voltage here, means the filter function better. Okay, and the ripple factor indicates the how efficient the filter is, and we can calculate the ripple factor, which is using this equation, which is VRPP over VDC, and VRPP refer to peak, okay, peak to peak ripple voltage, and VDC is DC average value for the filter output voltage. Okay, so for half wave rectifier, we can use directly, but for full wave rectifier, VP VRPP equals to 1 over frequency RLC, VP rectified, and VDC equals to 1 minus 1 over 2 FRLC VP rectified. Okay, so that is the rectifier. Okay, and then the diode also can be used as a Zener diode. So I hope you still remember when we discussed about the IV characteristic of diodes. We as shown here, which is we have forward bias here, and also we have reverse bias here. Okay, before it start to damage or it start to malfunction, it will go to the breakdown region. So in breakdown region, there are two types, which is the first breakdown happen is Zener breakdown, and then the second one is avalanche. But for Zener breakdown, we can take its advantage to fabricate a Zener diode, and the symbol of Zener diode is like this. Is a diode, but there is a, I don't know what to say, it's something like Nazi border. Okay, so there the silicon diode, actually when we fabricate this diode, it will optimize for the operation during the reverse breakdown region, because in the reverse part the breakdown will happen, and then it will set carefully by controlling the doping level during the fabrication. And when Zener diode is in forward bias, it behave like a normal silicon diode. Okay, and then we use a Zener diode in the voltage regulator, which is Zener diode in this voltage regulator will responsible for to hold the load voltage, to make sure the load voltage is constant, even though we change the voltage and the load resistance. Okay, and then there are few things, a few facts that we should know about Zener diode, which is we have IZ, okay, current for Zener, and then we have Zener voltage. So when Zener diode is in reverse bias region with a voltage less than VZ, it will block the current like a normal silicon. Okay, so this is VZ, I circle here VZ. And also when reverse bias reach VZ, the voltage is limited around this value, but can conduct a very large current. Okay, so now I want to discuss about characteristic curve for Zener diode, because the characteristic curve is similar to the silicon type or normal diode. Okay, but we will emphasize more at the region of at the region of reverse bias when the breakdown region happen. Okay, so the top diagram is for the ideal Zener diode. So this is the symbol of a diode, and then as I mentioned before, this is perfect, very perfect Zener diode. But I think we should discuss more on practical model characteristic curve for as shown in this diagram, in which the symbol of Zener diode is the same, but the Zener diode will attach to the power supply, and then we will have VZ. Okay, so come back to the IV characteristic curve. We refer to the breakdown region in which happen during the reverse bias, in which when the starting of declining in the current with the increment of reverse voltage, they will denote as IZ, which is a Zener knee current. Okay, and it will function well when they reach the IZ Zener test current, and it will reach to Zener maximum current, and after that it will damage. Okay, clear? And then we also can obtain the difference of IZ. Okay, so that's mean delta IZ, we can get the value before the IZM, because IZM is the maximum current, and then we will get ZZ equals to delta VZ over IZ. So this one Y axis is IZ, and X axis is delta VZ. Okay, so Zener equivalent circuit, we can see from this diagram, when we have IS, of course we have the source, voltage source, and then current from the voltage source across the resistor R, and then before it goes to Zener diode, and when the current is sufficient enough, the Zener diode will be function, and the value of the current will be IZ. And then we have switch here to off and on the connection of load, and then we have the current of load and the potential difference across the load. So Zener current, which is IZ, I already mentioned just now, is a minimum required current by the diode to regulate the voltage across the Zener diode. So the current, which is IS, will flow through the resistor, and the total current that is the circuit requires, and then we can get some of the current flow through the load and current flow through the Zener diode as IZ. So we can calculate IS using this formula, and this formula can be referred to this diagram. IS equals to IL plus IZ, and the voltage drop VR equals to difference voltage of difference potential for VS and VL, and the resistance we can calculate as a V equals to then we can calculate R equals to VR over IS, and the power power dissipation of the diode, we will get PIV, and P equals to IS times with VZ. Okay, and the lastly, we can calculate the power dissipation of the resistor, which is IS times with VR, and VR is VS of minus VL. Okay, for the application part of a Zener diode, okay, actually, I will discuss into two ways. Okay, the first one, Zener regulation with a variable input, and then the second one, regulation with a variable loops. So we go to the variable input. Okay, so in this diagram, we will have the output is, for example, here is 10. And then the value of resistance here is 220 ohm. Okay. And then this one is the code of the Zener diode. So from the fact sheets, we can obtain the maximum value for the Zener. Maximum value of voltage, of current, etc. Okay, so from this diagram, we can calculate VR, okay, for the resistor as IZ K. Okay, this one ZK just now is a knee here. ZK is a knee current. Okay, during the reverse region, in the reverse region, and then we can substitute the value. Normally, IZK will be given in the question. Okay, because that is the characteristic of the Zener diode with the this code. Okay, and then we plug in the value of a resistor, and then we can get the voltage for the resistor as 55 millivolts. And we also can calculate VR as V in minus V Zener. If let's say we don't have IZK, but we have the value of V Zener. So maybe V Zener 12 volts, something like that, and then we can calculate. That is a normal calculation when we have a difference in potential across a resistance. And then we also can calculate VR using IZM, just in case if IZM value is given. Okay, and this one we get 22 volt. So if we see from this value is logic, because IZK come IZK IZK happen first, okay, and IZM can be detected after IZK. So that is why the value of IZM VR of using IZM is bigger compared to IZK. And the V input minimum we can calculate using this equation, which is a voltage for R plus with a voltage from Z. Okay, and then we get this value after we calculate other parameter, and then V in maximum. Okay, so VE maximum, if you see from this equation, it use the maximum voltage calculated from IZM, because IZM is current for zener at the maximum level. Okay, and then plus with the output, which is become 32. So that is a simple calculation for the zener regulator with the variable input. So in another case, which is zener regulation with variable loads, okay, that means we can change the number of loads, okay, and then zener will maintain at constant voltage across as long the zener current is greater than IZK, which is a Ni, and less than IZM. So if we want to know where is the region, that means the region is in between. The region of current and voltage should be in this region. Okay. And then the total current through the resistance will be constant as long as the zener keep regulating the voltage. Okay. We can calculate the VZ, the zener voltage, which is we can calculate the IZ maximum. Okay, this one, this is the parameter given for this kind of zener diode. So for example, like IZ max, we want to know what is the value for this zener. The current, the maximum current can be applied to this zener voltage. So we can calculate from V input minus with VZ over the R, because V equals to IR from the Ohm's law, and then we get this value. Okay, and IZ max should be smaller than IZ M, which is this. If we get this one, that means the value is acceptable minimum value for the IL, because zener still can operate or can hold the current. So in that case, we also can calculate IL max, which is equals to IT minus IZ, and we will get this value. Okay. Another part, we also can calculate the load resistor minimum. Okay, so the minimum load resistor, okay, we will get from V equals to IR Ohm's law, and VZ, the zener voltage, divide by the current maximum through the zener. And finally, we get the value as 1171 ohm. So what is the meaning 1171 ohm here? That means this one is RL minimum. If RL is smaller than this value, it will cause more of total current away from the zener, and current for the zener diode will be reduced below IZK. Therefore, zener will lose the regulation properties. And the regulator properties will be maintained for any value RL between 1171 and infinity. So therefore, we can calculate RL min as V out divided by IL. Okay. Okay. Any question? Any question? Oh, akan see.
Next question.
Any question? Ada soalan? Any question? No.
Madam,
Is it okay?
Madam, what will be the chapters coming up in the next week test?
Come next. Oh, topic for test. Right?
Yeah.
Okay, it will be PN junction, energy band gap, and also semiconductor. And maybe half wave rectifier.
Okay, thank you, Madam.
No worries. Can we get this slide? Oh, definitely. I will upload after this in the spectrum. Actually, I want to upload yesterday, but I think it's better after. Okay, how many questions? Because our test is around 1 hour, okay, and is online. Okay, so I think will be around 5 to 6 questions. What else? PN junction, energy blanket, something itu, maybe, yeah. Can I have feedback for this? Just now class? The class just now? Is it okay? You can follow, or what difficulties that you are facing now to follow my lecture? Anyone? You can follow? Boy Lukman, no comment. Zinti can, okay, can manage. Devon, okay. How about others? Don't record. Bisa aja, okay. Is it MCQ question for the test? No? It is all calculation. No? Theory and simple calculation. Other question? Tips. Tips. Test. What else I should give the tips? Because I think already, I don't know, maybe I think you should aware the tips during the lecture, right? The tips, read about semiconductor materials, how the energy band gap, how the holes and electron being transported in the P and N junction when there is a forward bias, reverse bias, and the energy band diagram. Study, pandai. Okay, spot question. Just now spot lah already. Spotted. Okay, what else? Any question about full wave? Susah tak? To me, no. To me, no. I don't know to you. No. No question. Apa nak sendu, happy mah. You just read the lecture, refer to lecture notes, you know. I think my question is very direct, would be, what's the difference between Vmax and Vpeak? Okay, that one Vmax for Ripple. cannot record just now. When I want to record just now, Giselle, it, I don't know, it stuck right just now. Anyone record? Oh, suddenly tersharp. No, no. Are you sure? Help me. If you record, maybe I can upload in the Spectrum. Oh, Gigi. What is Gigi Angson? Ang. Oh, answer. Okay. VMAX and VPix. VMAX, VPix2, which one? What good game? VM and VPix2 in which part? Oh, Gigi tu good game. I don't know, maybe because last semester pula, last week